Good morning. Thank you for tuning into this talk. My name is Felix Ulrich-Oltean, and I'm just coming to the end of my first year as a PhD student at the University of York. Today, I will give you a short overview of my PhD project, which in a nutshell is to learn to make good choices when encoding CSPs into Boolean SAT formulae. I'm very grateful to the reviewers who read my summary paper submission for this doctoral program, and I've tried to address their points to some extent in this talk. So here's what's coming up. I will explain briefly the motivation behind using SAT to solve constraint satisfaction problems. We will look at a basic example of how encoding to SAT works and talk about the desirable features of such an encoding. Then I will take you through some of my early experiments, and finally I will sketch out how we plan to use machine learning in this process. So why translate a CSP into SAT? The table here shows the top of the rankings in the 2019 XCSP Constraint Solver competition. As you can see, the top 5 places are all taken by solvers which use SAT solvers as their back end. So this suggests that this approach is efficient and fruitful. SAT solvers themselves are becoming more powerful. This plot shows the performance of the winning solvers in the SAT competition over the last 2 decades. They've all been run on the 2020 set of benchmarks. And if we look at the legend here, the most recent winner is at the top. And here's the one from 2002. So the plot shows that year on year, the best SAT solvers have been able to solve more and more instances in the same amount of time. So by encoding our CSP into a SAT formula, we can continue to benefit from the ever-developing power of these SAT solvers. Let's consider in a bit more detail how encoding to SAT actually works. As an example, let's take a pseudo-Boolean summing constraint, which is a bit like the classic knapsack problem, in that we have a set of Boolean variables, or items if you like. Each one has an associated weight, and our knapsack has a capacity limit so that the total weight of the chosen items must not exceed that limit. Here we see a very basic CSP model file written in Essence Prime, and at its heart is the PB constraint. So the config matrix is our array of decision variables, and this line says that for any item which is set to true, when we sum up those weights, we must not exceed the upper limit. The tool we use, called Savile takes such CSP models. It applies various optimizations and reformulations and produces models suitable for a variety of backend solvers, such as dedicated constraint solvers like G-code or Minion, or for SAT solvers. So here is an example, the beginning of a SAT formula in conjunctive normal form, with each line showing a different clause. I will describe one encoding for a PB constraint. This one is called the generalized totalizer, and these illustrations are taken from the paper credited at the bottom there. The way this works is the tree structure represents our constraint. And so, for example, this inequality here has variables x1 through to x8 as our decision variables. The upper bound is 7, and 2, 2, 3, 5, etc. are the associated weights. And in the leaf nodes, we have SAT variables for each decision variable, and you can see they've been annotated with the weights of the corresponding decision variables. As we go up the tree then, each SAT variable at every node represents a sum that could have been reached. So for example, if D4 is set to true, it means we have reached a sum of 4, which in other words means that x1 and x2 must have been set to true. Notice that once we get past 7, we don't record those weights. We simply use a weight of 8 to mean anytime we have gone bust, we have gone past 7. So for example, at G, if both x7 and x8 were turned on, the total sum would be 10, but we don't record that, we just record 8. And that's the same throughout the tree. So to produce our SAT clauses, we have these different types of clauses. So the ones labeled 10 are basically saying that if a variable is turned to true here, then the variable with the same weight in the parent node is also set to true. So that's to percolate the sum up the tree. The number 9 clauses are saying that for any two variables in sibling nodes that are turned to true, the variable in the parent node that signifies that sum will also be turned to true. So for example here, if D2 was on and E3 was on, then B5 would be turned on. And finally, the clincher clause is this one, which states that A, in our case A8, must not be turned on. In other words, we must not have gone bust. The generalized totalizer is just one encoding for PB constraints. Now, different encodings have different properties. One obviously desirable property is the size. We want a small size of encoding, but we might also care about how well propagation works in that encoding. Many SAT encodings ensure that unit propagation maintains generalized arc consistency, for example. In this extract we see here from the same paper as the previous slide, 3 sets of problem instances have been run with 4 different encodings, and in the highlighted section, for instance, we can see that the BDD encoding has used 57,000 variables and 115,000 clauses, whereas SWC has used a few more variables and clauses. However, this one took less time to generate, and on average, for the median, the solving time was actually a little bit less. So I have done some exploratory experiments to see how different features of a problem instance affect the performance of different encodings. And initially I just started with a very basic model, a bit like the one we saw earlier, just containing a PB constraint. And I generated many different instances with variation in the number of coefficients, the extent of clustering in the coefficients, and also the relative size of the coefficients compared to the upper bound. And here we can see a visualization of 12 different instances. These all had 64 variables. And for example, as we go from left to right, the range that we were sampling the coefficients from has increased as a proportion of the upper bound. And as we go down the rows, there is more and more clustering. In other words, by the time we get to the bottom, each coefficient has several other decision variables with the same coefficient. So we end up with roughly root n groups, where n is the number of variables. I then ran Savile Row with each of the PB encodings that are available in turn, and was able to start looking for which aspects of the problem instance affected the relative performance of the different encodings. For example, in this graphic, if we look at the GGT encoding, which is the red one, we can see that as the coefficients became more and more clustered, this encoding became more and more competitive. So the ambition is to use features of the entire CSP instance and of the individual constraints within it to predict the best choice of encoding for the separate constraints in the problem. Initially, I'm working on a minimal prototype, and so to begin with, I've been using the Minizinc to features extractor, which analyzes the whole problem instance, and this tool extracts around 100 features and feature crosses. Again, then I run Savile Row to solve those problem instances with all the different encoding options for a particular constraint type. And then this has provided the labels of so-called best encoding for the learning algorithm. My first attempts have been using scikit-learn's random forest classifier and training it on a set of benchmarks that ship with the Savile Row source code. Here is a sample of the output after validation, but bear in mind it's a very tiny number of problem instances at the moment, so it was about 100 problems, and so the validation has been done on just 16 rows. So a major challenge ahead is to build a much larger data set of CSP instances to train on. I'm planning to do this by using constraint solving competitions and also industrial instances available for scheduling, timetabling, logistics, etc. Ultimately, the plan is to incorporate into Savile Row a classifier which decides the SAT encoding to use for a particular constraint in that instance based on the features of that constraint, but also on the features of the entire problem instance. And the hope is that this approach will perform better than the current setup where we choose offline which encoding to use for every constraint type. So thank you very much for listening, and I'll be happy to answer any questions.